Hello, Nate from Microchip Technology here to talk about the AVR SD's error controller. In safety-critical applications such as those following ISO 26262, IEC 61508, or any other safety standards, a major component of ensuring a design's safety and compliance is proper error handling. Errors, unexpected behaviors, and malfunctions are impossible to avoid 100% of the time. So, to ensure safety, these behaviors must be accounted for. Hence, the need for an error controller. The error controller serves as a central component in a design by monitoring and managing hardware errors reported within the MCU. Its primary role is to ensure system reliability by promptly detecting errors, notifying the application when those errors occur, and initiating appropriate responses when necessary. To support these functions, the error controller remains continuously active and provides configurable error severity levels. It's also capable of generating a heartbeat signal to indicate overall system health. These features enable the error controller to act as an effective interface between error detecting hardware and the application to help maintain safe and dependable operation. With that in mind, let's talk about how this error controller works. The error controller receives incoming errors flagged by other hardware, evaluates them based on previously assigned severity levels, enters a corresponding state, and acts according to that state. Think of it like a safety supervisor overlooking multiple tasks, and when a problem is reported, they quickly evaluate the problem and take appropriate action. These actions can be anything from giving a notification, sounding an alarm, issuing a microcontroller reset, or even as drastic as shutting down larger system operations if the AVR SD is the safety monitor of said system. A key aspect of how this feature functions is its use of error severity levels and the error controller states in response to an error. To make them easier to understand, both severity levels and the error controller system states are being simplified here. If you want to learn more, please read the corresponding section of the AVR SD datasheet linked in the description. Now, both the error controller system states and the error severity levels are closely tied together, so we'll be starting by covering the error severity levels. For now, just know that there are 4 system states: config, normal, alarm, and fault, and those will be covered in just a moment. Starting with the error controller's error severity levels, the error controller receives errors on error channels, and each channel has a user-configured severity. The lowest severity is notification. When an error is received on a channel configured for notification severity, the error controller will set a status bit to indicate a notification level error has occurred and set the corresponding status flag to indicate which channel the error occurred on. The next level of severity is non-critical. When an error is received on a channel configured for non-critical severity, the error controller will set a status bit to indicate a non-critical error has occurred and set its corresponding status flag to indicate which channel, similar to the notification severity level. However, in addition, the error controller will also enter its alarm state and trigger an interrupt. That interrupt may also be configured to be non-maskable, which should be used when an error needs to be addressed with the device reset. The highest level of severity is a critical error. When an error is received on a channel configured for critical severity, it will set its corresponding status bit and status flag like the previous 2 levels and enter its fault state. Now we've covered the severity levels, let's go back to the AVR SD's error controller's 4 system states. The first is the config state, which is used when configuring the error controller. Its exact behavior is outside the scope of this video, however details for it are provided in the AVR SD datasheet. The second state is normal. When not in the config state, this is the expected state when either no errors have been received or when only notification severity errors have been received. The third state is alarm. The error controller will switch to this state when a non-critical error is received. As mentioned earlier, a non-critical error will initiate a system interrupt to handle and log the corresponding error. If the timeout timer is enabled, then this will also start counting down, and if the error is not cleared within the timeout period, the controller will transition from alarm to fault. This period may be configured by the user to a maximum of 1020 clock cycles. If the timeout timer is not enabled, then it will bypass the alarm state and go straight to fault. The fourth and final state is the fault state. The error controller enters this state when either a critical severity error is received by the error controller, or if the error controller is in an alarm state that times out. When the error controller enters its fault state, it takes multiple actions to ensure the MCU enters a safe state. The error controller will request a device reset and set the error controller reset flag to signal that reset has occurred. Any error controller heartbeat will stop, and all AVR SD I/O pins will be floated, or in other words, set to high impedance. Speaking of the error controller's heartbeat and ability to float pins, let's briefly discuss those features. The error controller on the AVR SD has the ability to output a steady 1 kHz square wave to an I/O pin as a way of signaling to other devices the health of the AVR SD. This signal is the device heartbeat, and just like any living thing with a heartbeat, if it suddenly stops, there's a big problem. But unlike something living, when the device heartbeat stops, it acts as a way to easily warn other devices in a design of an issue. Regarding the error controller's ability to float pins, this is a feature that can be enabled for any error channel of any severity. However, critical errors will always activate this feature. When certain or especially severe errors occur within a system, unintended signals from a device's I/O pins can potentially cause more issues elsewhere. Floating I/O pins gives the designer a known state for all I/O pins that quickly sever connections to keep errors contained. So how can these features be expected to work in practice, and how do all of these systems interact when an error occurs? Well, say we have a hypothetical application using the AVR SD and its error controller, and its error controller has the following configuration. The heartbeat is enabled, the alarm timeout is enabled and set to timeout after the maximum 1020 clock cycles, the OPC error channel that monitors for illegal CPU opcodes and parity errors on the instruction bus is configured as critical, the SWDT error channel that monitors for issues with the synchronous watchdog timer is set as non-critical, and when an error is received, the controller will initiate a regular interrupt to reset the SWDT peripheral and clear the appropriate error flags. And the EEPROM channel that monitors for EEPROM bit errors is set as notification. While the system runs normally, no error flags are raised, and the heartbeat will continue to output its 1 kHz square wave to a pin. When a peripheral or other hardware with a connection to the error controller detects an error, it raises its own error interrupt flag, which is then received by the error controller. Now let's use the example channels we defined earlier to see what happens once the error controller receives these errors. If an error is received on the EEPROM channel, the error controller remains in the normal state, and it will set its notification bit in the error controller status A register and the corresponding channel bit in the error controller ESF register to indicate that a notification level error has occurred, and that it occurred on the EEPROM channel. If an error is received on the SWDT error channel, the error controller enters its alarm state. It will set the non-critical bit in error controller status A and the SWDT channel bit in error controller ESF. The interrupt resets the SWDT while the error controller timeout timer counts for 1020 clock cycles. If the SWDT is successfully reset and the issue is resolved before the completion of those 1020 clock cycles, then the device may return to its normal operating state. If the error is not successfully cleared, then the device will transition to its fault state and subsequently request an error controller reset, stop the heartbeat, and float the I/O pins. Finally, if an error is received on the OPC error channel, the error controller will enter its fault state on its next clock edge. Set the critical bit in error controller status A and the bit for the OPC channel in error controller ESF. Then, the error controller will request an error controller reset, stop the heartbeat, and float the I/O pins. Now that we've covered how the error controller works and examples of how the system would react in certain circumstances, let's go over some general guidelines to keep things running smoothly. First, when clearing error flags, clear the error flag from the source of the error first, then clear the error controller flags. Otherwise, the source error flag will re-trigger its channel on the error controller. The error controller requires a clock to function and can't function in the power down or standby sleep modes. It can only function while it is in active with no sleep mode or in idle. Errors specifically from the dual-core lockstep CPU cores mismatching are not sent to the error controller and are handled separately. For non-critical errors and the alarm state, when possible, always use non-maskable interrupts if the AVR SD needs to reset to handle an error. and never disable the timeout timer and choose a large enough value to cover appropriate error handling. Lastly, while developing a project, it is easiest to set all channels to notification severity for easier debugging. The last feature we'll be covering is error injection. Error injection is featured on multiple modules inside of the AVR SD, the most obvious example being the error injection included as part of the error controller to test its exact behavior in an application. However, error injection functionality is also present for most source channels feeding into the error controller and many other features on the AVR SD. To name a few, this includes the AVR SD dual-core lockstep CPU, the ECC protected memory, its cyclical redundancy check peripheral, clock controller, and more. The AVR SD's error injection features offer significant benefits for safety-critical designs, and by using it, designers can verify that safety mechanisms for their design operate as intended. This helps ensure system reliability, compliance, and provides an easy and accessible method for conducting these critical tests, which streamlines the validation process and makes development easier and faster. Additionally, error injection testing is a mandatory requirement in many functional safety standards such as ISO 26262, making the AVR SD's built-in support invaluable for achieving certification and meeting industry regulations. Error injection's benefit lies in the fact that testing for latent faults or uncommon cases poses a particular design challenge. Many of the errors are not going to be common or easy to replicate, and inducing a specific error for testing isn't necessarily as easy as simply flipping a switch. Without specialized hardware, the designer may have to create their own tests from scratch with strategies like simulating peripheral failures, rewriting pieces of memory, so on and so forth. That's where error injection features come in handy because it provides a simple way built into the AVR SD to generate an error. In the case of the error controller's error injection features, this is done by writing one or multiple bits in their corresponding error injection channel. Each error injection mechanism on the AVR SD will work slightly differently, however, so make sure to refer to the appropriate peripheral in the AVR SD datasheet for how to approach error injection in your application. The good news is you don't need to be a seasoned functional safety or development expert to use all these features. The hardware features make error injection testing far more accessible to developers, and to supplement these features, we also provide an AVR SD safety framework that can be found on the AVR SD family page, linked below in the description for a structured software library setup to use these features. That covers how the AVR SD's error controller detects, manages, and tests faults in an application. If you want to learn more about functional safety, our functional safety courses are available on Microchip University. If you want to get started developing on the AVR SD, you can start with its Curiosity Nano development board. And if you want to learn more about the AVR SD, check out its family page where you can find more information and the device datasheet. This series' previous video on how the AVR SD helps achieve ASIL C and SIL 2 compliancy, and stay tuned for our next video covering how the AVR SD protects and preserves its memory for safety-critical applications. Thanks for watching, and if you like this content and want to see more, please don't forget to like, comment, subscribe, and ring the bell while you're at it for notifications on any future videos.